Welcome to this rigorous scientific lecture on the physics and chemistry of rice clumping. Today we're going to explore why rice can form sticky masses or stay separate, depending on type and preparation method. Let's start with the fundamental question. What determines whether cooked rice grains stick together or remain separate? The answer lies in two interconnected phenomena: granular mechanics and starch gel formation. First, we must recognize that rice is a granular material. Each grain is a discrete particle, and the bulk behavior emerges from interparticle interactions. This falls under the domain of granular mechanics, a fascinating branch of physics. Second, rice grains contain starch polymers that undergo dramatic transformations during cooking. These transformations create adhesive forces between grains through gelatinization and retrogradation processes. Let's begin with granular mechanics. Consider a pile of rice grains. Each grain has dimensions on the order of 5 to 7 millimeters in length and about 1.5 to 2 millimeters in diameter. In a pile, each grain experiences gravitational force downward, normal forces from neighboring grains, and frictional forces at contact points. The angle of repose, typically 30 to 35 degrees for dry rice, reflects the balance of these forces. Experimental measurements show that the coefficient of static friction between dry rice grains is approximately 0.4. This means a grain will begin to slide when the tangent of the contact angle exceeds this value. Mu sub s equals the frictional force divided by the normal force, approximately 0.4 for dry rice. Now here's an important question. How does the presence of water change these granular mechanics? Let's think about this systematically. Initially, when water is present between grains, it acts as a lubricant. The coefficient of friction can drop to 0.1 or even lower. This is why wet rice flows more easily than dry rice. However, water also enables chemical transformations. At elevated temperatures, starch molecules on the grain surface dissolve and form a viscous gel layer. This changes everything. Let's dive into the starch chemistry. Rice contains two types of starch: amylose and amylopectin. The ratio of these determines the stickiness behavior. Amylose is a linear polymer with molecular weight around 100,000 daltons. Amylopectin is highly branched with molecular weight up to 100 million daltons. Most rice contains 20 to 30% amylose and 70 to 80% amylopectin. Sticky rice, also called glutinous rice, contains less than 5% amylose. This high amylopectin content is crucial for its sticky behavior. Long grain rice typically has 22 to 28% amylose. The higher amylose content promotes grain separation after cooking. Now let's examine gelatinization. When rice is heated in water above approximately 68 degrees Celsius, a phase transition occurs. The crystalline structure of starch granules breaks down. The gelatinization temperature ranges from 68 to 78 degrees Celsius, depending on the rice variety and amylose content. Before heating, starch granules have an organized crystalline structure. After gelatinization, water penetrates the granule, hydrogen bonds break, and the structure swells dramatically. The granule can absorb 200 to 300% of its weight in water. Volumetrically, the starch granule swells by a factor of 5 to 10. This swelling exerts pressure on the cell walls of the rice grain. Here's our next question. What exactly creates the sticky surface layer that causes rice grains to adhere? The answer involves leaching and gel formation. During cooking, amylose molecules, being linear and smaller, leach out from the grain surface more readily than the highly branched amylopectin. This creates a surface gel layer. The viscosity of the gel layer scales with concentration to approximately the 3.5 power. This is a characteristic of semi-dilute polymer solutions above the overlap concentration. Measurements using confocal microscopy show the surface gel layer is typically 10 to 50 micrometers thick. This may seem thin, but it's sufficient to bridge the gap between adjacent grains. Let's perform a back-of-the-envelope calculation. What is the adhesion force between two rice grains mediated by this starch gel? We can model this scenario as a liquid capillary bridge between two spherical particles. The adhesion force depends on surface tension and contact geometry. The adhesion force is approximately 2 pi r gamma sine theta, where r is the contact radius, gamma is surface tension, and theta is the contact angle. Let's estimate. Contact radius r is approximately 500 micrometers, or 5 times 10 to the negative 4 meters. The surface tension of the starch gel is approximately 0.05 newtons per meter, and sine theta is roughly 0.5. Plugging in, F approximately equals 2 times 3.1, 4 times 5 times 10 to the negative 4 times 0.05 times 0.5. This gives us approximately 8 times 10 to the negative 5 newtons, or 80 micronewtons. This is a small force, but there are many contact points. A single rice grain in a clump may have 6 to 12 contact points with neighbors. The total adhesion force is then 500 micronewtons to 1 millinewton. Total force equals 500 to 1,000 micronewtons. Compare this to the weight of a single rice grain. A single rice grain weighs approximately 20 milligrams, which is 2 times 10 to the negative 5 kilograms. Its weight force is mg equals 2 times 10 to the negative 5 times 9.8, approximately 200 micronewtons. Weight of grain equals 2 times 10 to the negative 5 times 9.8, approximately 200 micronewtons. The adhesion forces are comparable to or even greater than gravitational forces. This explains why sticky rice forms cohesive clumps that can support their own weight. Now let's connect this to practical rice types and cooking methods. Different varieties and techniques manipulate these physical and chemical principles. Jasmine rice has medium amylose content around 18 to 20%. It exhibits slight stickiness, but grains remain largely separate. This is due to moderate surface gel formation. Basmati rice has high amylose content, 22 to 28%. The grains stay very separate because amylose, despite leaching out, forms a less sticky gel than amylopectin-rich surfaces. Sticky rice with less than 5% amylose produces maximum clumping. The nearly pure amylopectin surface creates an extremely adhesive gel layer. Here's a practical question. Why does rinsing rice before cooking reduce stickiness? The answer relates to removing surface starch. Rinsing removes loose starch dust that coats the grains from milling and transport. This dust, when hydrated, creates additional adhesive material between grains. Before rinsing, loose starch particles coat the grain surfaces. After rinsing, these particles are washed away, leaving cleaner grain surfaces that will produce less surface gel during cooking. Controlled experiments show that 3 rinses can remove 20 to 30% of readily available surface starch. This significantly reduces the stickiness of the final product. The water-to-rice ratio also dramatically affects texture through both thermodynamic and kinetic factors. Let's analyze this quantitatively. With excess water, more starch leaches from the grain, but the concentration in the surrounding liquid is diluted. The surface gel layer is thinner and less viscous. With minimal water, just enough for complete absorption, the starch concentration remains high. The resulting gel is more concentrated and more adhesive. Typical water-to-rice volume ratios range from 1.5 to 2.5, depending on desired texture. Lower ratios produce stickier rice. Now let's discuss retrogradation, the process by which gelatinized starch recrystallizes upon cooling. This is thermodynamically favorable, but kinetically slow. After cooking, as rice cools, amylose chains begin to reassociate through hydrogen bonding. This retrogradation process increases stiffness and reduces stickiness over time. The retrogradation rate constant follows an Arrhenius relationship, K retro proportional to exponential of negative E sub A over RT, where E sub A is the activation energy, approximately 60 kilojoules per mole. At room temperature, the characteristic time for 50% retrogradation is approximately 2 to 6 hours. This is why leftover rice becomes firm and less sticky. Refrigeration actually accelerates retrogradation because the thermodynamic driving force increases at lower temperatures, even though kinetics slow. The optimum retrogradation temperature is around 4 degrees Celsius. Let's use an analogy. Rice grains in water with dissolved starch can be viewed as a colloidal system with depletion forces and bridging interactions. When polymer concentration is high, there's an entropic driving force for particles to aggregate. Polymers are excluded from the gap between particles, creating an osmotic pressure difference that pushes particles together. The depletion force scales approximately with the square of polymer concentration. This explains the dramatic increase in stickiness at high starch concentrations. depletion force, proportional to concentration squared, times polymer radius cubed. For starch, this can generate forces of tens of micronewtons. Now let's synthesize this knowledge into practical process control strategies for engineering rice texture. To maximize grain separation, select high amylose rice variety, rinse thoroughly to remove surface starch, use excess water during cooking, and fluff immediately after cooking to disrupt contact points. To maximize stickiness, select low amylose glutinous rice, skip rinsing to retain surface starch, use minimal water absorption method, and allow slight overcooking to maximize starch leaching. Here's a summary of process parameters. On the left, conditions for separate grains. On the right, conditions for maximum stickiness. These represent opposite ends of the texture spectrum. Can we quantify the texture difference? Yes, using rheological measurements and texture analysis. Texture analyzers measure parameters like hardness, the peak force during compression, and adhesiveness, the work needed to pull a probe away from the sample. Sticky rice typically shows lower hardness values because the starch gel lubricates grain boundaries. Hardness of sticky rice is less than hardness of separate grain rice. However, adhesiveness can be 5 to 10 times higher for sticky rice. This quantifies the dramatic difference in clumping behavior. Let's perform a scaling analysis to connect single-grain adhesion to bulk mechanical properties. This is an important bridge between microscopic and macroscopic behavior. Consider a cubic volume of cooked rice containing n grains. Each grain has approximately z nearest neighbors, where z is the coordination number, typically 6 to 8. The number of grains n equals the bulk volume divided by phi times the grain volume, where phi is the packing fraction, approximately 0.6 for random close packing. The total adhesion energy in the system scales as n times z times the adhesion energy per contact. This is the energy required to completely separate all grains. E total equals 1/2 NZE contact. The factor of 1/2 avoids double counting each contact. Let's estimate for 1 cubic centimeter of sticky rice. With approximately 30 grains, Z equals 7, and contact energy of 10 nanojoules, we get total energy around 10 millijoules. E approximately equals 30 times 7 times 10 to the negative 8, approximately 10 to the negative 5 joules or 10 millijoules. This is measurable with sensitive calorimetry. Let's zoom down to the molecular level. The fundamental interaction is hydrogen bonding between starch molecules across the gel layer separating grains. Starch chains form helical structures stabilized by intramolecular hydrogen bonds. At the interface between grains, intermolecular hydrogen bonds between chains on opposing surfaces create adhesion. Each hydrogen bond contributes approximately 20 kilojoules per mole of binding energy. With Avogadro's number, that's 3.3 times 10 to the negative 20 joules per bond. E hydrogen bond equals 20,000 divided by 6.02 times 10 to the 23, approximately 3.3 times 10 to the negative 20 joules. To achieve our estimated 10 nanojoules per grain-grain contact, we need approximately 300 million hydrogen bonds. This seems large, but is reasonable for a contact area of tens of square micrometers. This corresponds to a surface density of about 10 to the 18 bonds per square meter, or 1 bond per square nanometer. This is consistent with closely packed polymer chains. Environmental factors like temperature and humidity also affect rice texture post-cooking through their influence on retrogradation kinetics. At elevated temperatures, say 60 degrees Celsius, retrogradation is essentially frozen because thermal energy prevents stable crystallite formation. Rice remains soft and sticky. At refrigeration temperatures around 4 degrees Celsius, retrogradation proceeds at maximum rate. This is the temperature of minimum starch stability. Low ambient humidity accelerates surface drying, forming a dry crust while the interior remains moist. This creates texture gradients within each grain. Interestingly, Eastern and Western culinary traditions have evolved different approaches to rice texture, reflecting cultural preferences in different varieties. East Asian cuisines often favor medium-grain rice with slight stickiness. This texture is ideal for eating with chopsticks, as grains cohere into manageable clumps without being gummy. Western cuisines traditionally favor long-grain rice with well-separated grains. This texture is suited to eating with a fork, where individual grains are preferred. These culinary preferences have driven rice breeding programs in different directions, selecting for different amylose contents and grain geometries, optimized for the desired texture. Let's delve deeper into retrogradation thermodynamics. This process involves a competition between enthalpy and entropy. The Gibbs free energy change equals delta H minus T delta S. Retrogradation is enthalpically favorable due to hydrogen bond formation but entropically unfavorable due to loss of conformational freedom. At high temperatures, the entropy term T delta S dominates, and the disordered gel state is thermodynamically stable. Retrogradation does not occur. At low temperatures, the enthalpy term dominates, and crystallization becomes favorable. However, kinetics may be slow due to reduced molecular mobility. The transition temperature, where delta G equals 0, is approximately 50 to 60 degrees Celsius, depending on starch concentration and composition. These principles have practical implications for reheating leftover rice. Understanding the physics helps us restore desirable texture. Microwave reheating with a small amount of added water can partially reverse retrogradation. The added energy and moisture disrupt the reformed crystallites. Steaming is even more effective because it provides both heat and continuous moisture. This more completely regelatinizes the starch. However, complete restoration to the original fresh-cooked texture is impossible. Some irreversible retrogradation and moisture loss have occurred at the molecular level. Here's a culinary question. Why do fried rice recipes specifically call for day-old rice? The answer lies in moisture content and grain structure. Day-old rice has lost surface moisture and undergone partial retrogradation. The grains are firmer and less likely to break during high-heat stir-frying. The reduced surface stickiness prevents excessive clumping in the wok. Each grain can be individually coated with oil and seasonings. Fresh rice, being softer and stickier, would become mushy under the intense heat and mechanical agitation of wok cooking. It would also stick to the metal surface. Let's summarize this multiscale picture of rice texture. We've connected molecular-level hydrogen bonding to macroscopic mechanical properties. At the molecular scale, hydrogen bonds between starch polymers provide the fundamental adhesive interaction, with energy around 3 times 10 to the negative 20 joules per bond. At the microscale, surface gel layers and capillary bridges between grains create adhesion forces of tens to hundreds of micronewtons per contact. At the mesoscale, granular mechanics and coordination number determine how individual grain-grain contacts combine to create bulk mechanical properties. At the macroscale, bulk rheological properties like hardness, adhesiveness, and cohesiveness determine texture as perceived by the consumer. Each scale influences the next in a cascade of structure-property relationships. Understanding these connections allows rational manipulation of rice texture through variety selection and process control. This analysis exemplifies the broader field of food materials science. Rice is just one example of how fundamental physics and chemistry govern culinary properties. Similar principles of starch gelatinization, retrogradation, and granular mechanics apply to pasta, bread, and many other starch-based foods. The field is rich with opportunities for quantitative understanding. Modern food engineering increasingly uses rigorous rheology, colloidal science, and polymer physics to design products with specific textural properties. This fundamental understanding enables innovation, from breeding new rice varieties with tailored starch composition to developing novel cooking methods that precisely control texture. In conclusion, rice texture is determined by a beautiful interplay of granular mechanics and starch polymer chemistry. The ratio of amylose to amylopectin is the primary compositional variable. Low amylose means high stickiness, high amylose means separation. The cooking process controls the extent of starch gelatinization and surface starch leaching, which determine the properties of the adhesive gel layer between grains. Post-cooking storage conditions affect retrogradation kinetics, and therefore the time evolution of texture after cooking. Armed with this quantitative understanding, we can rationally predict and control rice texture through informed choices of variety, cooking method, and storage conditions. This transforms an empirical culinary art into a science-based engineering discipline.